All right, well, these are your basic notes for acids and bases, just like what you would have heard for in class. I apologize for my voice still all being all nasally, but anyway, here we go. I want to keep this brief. So, acids. There's a couple different ways to define an acid. The one you guys know best is this guy down here. Acids always start with H+. A substance, an acid can also be looked at as a substance that donates a hydrogen ion, H+, to another substance. We're going to look at that one in a minute. Finally, acid is also looked at as a molecular substance that dissociates. The word dissociates means breaks up in water to produce the H+, or another word for H+, is a hydronium ion. The hydronium ion's formula is H3O+. We'll see what that means in just a minute. All right, well, as you guys know, there's strong acids, really dangerous ones, and then there's weak acids. Strong acids, there's 6 big ones that you would want to know. Of course, the first acid that comes to mind, I'm sure, for everybody is this one, HCl. That's hydrochloric acid. Okay, and you guys can write the formulas down if you want to. Hydrochloric acid. Okay, another one, hydrochloric acid has 2 more tricky friends. They're in the same family on the periodic table. HBr, which you guessed it, is called hydrobromic acid. You can write that down if you want. And then finally, the last one, this one's really hard to say, but it's the next one in the halogen family. So it's Hi, and it's called hydroiodic acid. I'll spell that one for you. Hydroiodic. Okay? Those guys all sort of go together. There's a couple other strong acids. Probably the ones that come to mind as being really dangerous. So you might think of H2SO4. That's sulfuric acid. Okay, sulfuric acid. Just to remind you guys how it works, SO4 2 minus. Okay, that's the sulfate ion, has a 2 minus charge, so you need 2 H pluses to balance it out. Okay, so that's why it's H2SO4. Another strong acid is nitric acid. Nitric. Okay, and finally, the one that most people forget all the time is perchloric acid. Comes from the perchlorate ion, okay, which is on your polyion list, and you just have to balance it out with an H at the front. We'll talk a little bit more about naming down the line, but these are the 6 strong acids. What makes them strong is that they dissociate, or it breaks apart into ions, 100% in water. They totally break apart. Okay, and the way that we show that is if we were going to write out a general formula, okay, is HA, that might represent any of these acids up here. It's got the hydrogen, and then it's bonded to A. And we show that it's going to break up totally into H plus and A minus. Okay? So, we're going to practice that. So we're going to look at HCl. There's 2 different ways you can write it out, the shorthand way and the longhand way. This right here is more or less the shorthand way, which just is you taking HCl and breaking it up. Okay, so if you were smart, you would pause the recording right now. Sorry about that. You would stop the recording and try it yourself, and then check the answer. Okay, HCl, and it breaks up into H plus, and then Cl minus. Okay, now the longhand way, this is a little bit tricky. This is what's really happening in the acid solution. Now that H plus doesn't just break off, it goes someplace. Okay, and the other definition for an acid was that an acid is a substance that donates an H plus, right? Well, where is it donating this H plus? Well, that's where water comes into play. So in this solution, this aqueous solution, you have all this water, and you know what? The HCl, it's going to lose that H plus and it's going to donate it to water. Okay, so when that happens, well, if you take water and you give it one more H, that's where you get the hydronium ion. So it's H3O, and then because you gained an additional H plus, it's got an overall positive charge. And then just the same, the Cl minus is sort of left at the end. Okay? So that's the shorthand and the longhand way. They're both great. The longhand way is what's really happening. The shorthand way, though, is sort of simpler for us to write. Okay, so I would make sure that you can recognize both ways. All right, well, you guys, that's strong acids in a nutshell. Now, what about weak acids? Well, weak acids are any acid that's not one of the big 6. Okay, so I'm sure you guys can come up with a couple examples. Some of the really common ones might include acetic acid. So you take the acetate ion, C2H3O2 minus, and you put an H in front. So this whole thing is this acetic acid. That's what vinegar is. Basically, if you can in any way consume the acid, it's probably weak. So acetic acid, we talked about the fact that there's phosphoric acid in Coke. So phosphoric acid comes from the phosphate ion, which has a 3 minus charge. So you need 3 H's to balance it out. So that's phosphoric acid. Another one, well, let's see. We talked about HCl, we talked about HBr, we talked about HI. What about HF? HF, oddly enough, is a weak acid as well. Okay. Let's see, citric acid, you can list a bunch of other ones, okay? But if it's not one of the big six, it's definitely weak. So what makes a weak acid weak? Well, they don't react as much. They're not as dangerous usually. Weak acids do not dissociate 100% water. Oops, having some trouble here. My airliner turned off. Sorry about that. Okay, so weak acids do not dissociate 100% in water. So we actually use a double arrow to show this, to show that the reaction does not go to completion, or it's an equilibrium situation. We're not going to worry too much about equilibrium right now, but if you take AP Chem, you're going to learn a whole heck of a lot more about it. So the general format is basically the same thing, except this is my weak acid. It's still going to break up into H plus and A minus. It's just not going to do it as well. So we use this double arrow to show that. What that means is that the HA does break up a little bit, but then the H plus and the A minus, well, they get back together, and they go in this reverse direction. So that's what equilibrium means, is that you kind of have a forward and a backwards direction. When I think of equilibrium, I always think of like boyfriend-girlfriend situations. You guys probably know that couple that they break up, but then the next day they get back together, and you just never know if they're really broken up or gotten back together. Hope that you're not involved in that couple, but nonetheless, it might help you sort of understand what's going on with weak acids. All right, so let's do an example. We're going to show the dissociation, okay, or the breaking up of this weak acid, acetic acid. So the shorthand way, remember, all you have to do is show the H coming off, okay? Now again, if I were you, I would pause, and I would try both the shorthand, the longhand way, and then check your answer. So there's my double arrow, and then the H plus. Okay, so that would be the shorthand way for acetic acid breaking up. Okay, and then the longhand way is, of course, showing how the acetic acid actually interacts with the water. So I'm still going to use that double arrow to show that the reaction doesn't happen all the way. I'm going to make the hydronium ion. Okay, and there's the rest of the acetate ion. Okay? By the way, up here, way at the top, it says, what is a hydronium ion anyway? I hope you understand that now. That a hydronium ion is really a water molecule, right? There's a regular water molecule with an extra H. Okay, and when you put that extra H on, the whole molecule is now an ion, and it has a +1 charge. Okay? But for our purposes, we just say that a hydronium ion is more or less just an H+, because we don't care about the water. Okay, so for our purposes, hydronium ion and H+ are the same thing. Alright, this part is super easy, okay? Monoprotic, diprotic, polyprotic. Okay, well, mono means one, right? So it's any acid that only has one acidic hydrogen. Diprotic, 2 acidic hydrogens, and polyprotic, more than 2, okay? The only thing I want to point out is that if it's an acid, then the H's are written out in the front. If there's other H's, they might just be along for the ride. So for instance, this guy here, we got this H in the front, and then we got these H's. These H's here, just along for the ride. They're not acidic hydrogens. We would call this acid acetic acid. We would call this monoprotic. Okay? HCl, well, this is where I would pause, and I would try these. Okay, so here's the answers. HCl, monoprotic. H2SO4, diprotic. H3, blah, 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 polyprotic. This is actually citric acid. H2, diprotic. And this guy. Even though it has all kinds of H's, only the H in front count. Sorry about that. So this is monoprotic. Great! I told you guys this stuff was pretty easy. Here's a great example, and honestly, I would love it. I paused and tried to do these examples, and then listened to the answer and checked your work. Did you pause? Hopefully you did. Alright, so what the question is asking is for you to look at these two solutions and decide which solution would represent a strong acid, which solution would represent a weak acid. I'm hoping that you decided that scenario 1 was the strong acid. Okay, and scenario 2 was weak. Okay, why? Well, in the strong acid, what do you notice? The A and the H plus are broken apart. Okay, and in strong acids, when you put the acid in water, the H plus and the A minus totally break apart. Okay? But in the weak acid, you notice in a lot of cases, the H plus and A minus are still stuck together. Okay, that's the nature of a weak acid, is that it does not break up as well. Okay, or if it does break up, the H plus and A minus get back together. So this might be a solution of maybe HCl, this might be a solution of vinegar, maybe. Okay, I hope you got that right. Right, so this other practice, which of the following are weak acids? Alright, well this guy's out because it doesn't even start with an H. That's actually ammonia, which is a weak base. These guys are definitely all acids. Alright, HBr, that's one of the big six. Bye-bye. This guy we talked about a minute ago is phosphoric acid. Well, I can consume that. That's in like Coke or Pepsi, right? So this one's a weak acid. And this one, I've never seen it before. It's not one of the big six. It definitely starts with an H. So this is a weak acid too. Did you get those right? I hope so. I'm trying to keep this quick. Alright, so the last topic, bases. Well, if you understand acids, bases are super easy. So what are they? Well, acids are all about H+. Bases are a substance that produces a hydroxide ion, so they're all about OH-. Okay? So it's a compound that, well, acids donate the hydrogen ion, so guess what bases do? They accept the hydrogen ion from another substance. How do you recognize bases? This is probably the most important part. A metal hydroxide. Or ammonia, which is actually NH3. Okay? So strong bases, all metal, alkali metal hydroxides. Alkali metals are in family 1 on the periodic table. Okay, so what would be some examples? Let's see, sodium hydroxide, lithium hydroxide, potassium hydroxide, you could go down the list. Most of the alkaline earth metals are strong too. Barium hydroxide, calcium hydroxide, strontium hydroxide. Okay, so again, it's a metal hydroxide. Well, no surprise, strong bases dissociate or ionize into ions 100% in water. So we're going to use that nice little single arrow. So NaOH, put this bad boy in water. It's going to break into Na plus and OH minus. Okay? Now this one's a little trickier. It's barium hydroxide, OH2. So it's going to break into barium 2 plus, but how many OHs are you going to get out of this one? 2 OH minus. Okay? So the great thing about this is that barium hydroxide produces 2 OH minuses for every barium hydroxide. So you could say that barium hydroxide is a stronger base than sodium hydroxide. Barium hydroxide produces more OH minus. And the more OH minus you have, the more basic the substance. Alright, you guys are doing great. Last but not least, weak bases. Well, the great thing about weak bases is for our purposes, there's really only one example. And that example is ammonia, NH3. Okay? Most other weak bases involve nitrogen very often, but NH3 is the simplest one. Just like weak acids, weak bases do not dissociate 100%. So, guess what kind of arrow we're going to use? Okay, we're going to use a double arrow. Now, if you're going to show ammonia dissociating in water, you have to write the water. There's no shorthand way to do this. Why? Because whereas strong acids donate an H+, whereas strong and weak acids donate H+, weak bases accept H+. So they have to be able to get the H+ from somewhere. Where do they get that H+? It's from water. So water is going to donate the H+, and when the base, ammonia, accepts the H, it becomes NH4. CO4 is it gained an H from water with a positive charge. What's left of the water? Well, it lost an H, kind of acting as an acid, which you guys will see in your homework that water can act as an acid or a base, depending on the situation. It's going to make ammonium, and what's left of the water is OH minus. Well, that is what makes ammonia a base, and I will show you guys that in class. Okay? Well, the last thing we need to do, oh shoot, all the answers are there. So hopefully you guys paused it and checked your answers, but was to label these. I meant to erase those before I did this. So HClO4, that's one on the big six. So that's a strong acid. Iron hydroxide, strong base. I actually disagree with that answer. It's actually a weak base. I'm not sure who made this answer key, actually. Only because it's not one of the alkaline metal hydroxides or alkaline earth metal hydroxides. Probably not a big deal. It definitely is a base, but it's a weak base. H2CO3 is a weak acid. Magnesium hydroxide, strong base. HF, weak acid because it's not one of the big six. Finally, NH3 is a weak base. Okay, which we just talked about that. So that's really the one you need to know. This one, it's probably just sort of a bad question, really. That's a little beyond the scope of what we're doing right now. Alright, well guess what? That is the end. Sorry about my nasally voice. Okay, if you have some questions, we'll certainly take them in class. Pretty soon, later on in the week, we're going to do some practice where you'll want to refer back to these notes, and we'll see how you did with it. Thanks a bunch. See you.